Alright, welcome back. We are trying to find the continuous time Fourier transform. I've got two examples here. The first one is exactly that, find the Fourier transform of the impulse. And then the other one is a little bit different. It's find the signal whose Fourier transform is the impulse in frequency. So you see, in one case we have the impulse in time, in the other case we have the impulse in frequency. Let's get started. So for this top one, the first example, we need the analysis equation. We need to end up with x of j omega. And so the analysis equation says that you give me x of t, and then take it, multiply it by e to the minus j omega t, integrate over all time, and that gives me the Fourier transform. So now I put in the impulse for x of t like this. And the million-dollar question is, what is this integral equal to? Well, ladies and gentlemen, we need the sifting property there. The sifting property of the impulse. So if you don't remember that, take a look at that in a previous video a long time ago. The value of t that makes the impulse non-zero is 0, so we plug in 0 into what's multiplying the impulse. E to the 0 is 1, so that sifts out that value and we just get 1. That's nice. And so it sounds kind of ridiculous actually, but let's plot that. Okay, and of course 1 is a real number, right? And so we only really need one graph to plot this thing. And let me do that. It's tough, I know. Bring out your calculators if you need them. There's the plot of 1 for all omega. And I'm plotting that to make a point that I'm going to make in a second when we do the second example. So that's the answer. The answer is 1. Now, moving on to the next example, find the signal whose Fourier transform is the impulse. So here we need the synthesis equation. Give me the transform, and I will synthesize back. I need a 1 over 2 pi there, right? And then I need the x of j omega here, e to the positive j omega t, d omega is the equation that we need there. And so I'll keep my 2 pi there, 1 over 2 pi. I'll put in the impulse here, d omega, or delta omega, e to the j omega t d omega. And again, from the sifting property, ladies and gentlemen, check that out if you are still not entirely sure about it. Check it out, go back to the video. Anyway, omega equals to 0 is the value that we need that gets sifted out. So e to the 0 is 1, and then we have the 1 over 2 pi, and the answer to this question is this signal, which is really not a signal at all, or it's a constant signal, and it feels weird to say, but let me plot this signal. And so I've got t over here, and I know it's very difficult to plot this, but we're going to do it anyway. Whew. 1 over 2 pi, right? That's x of t. X of t is right here. Okay, so now, why did we do those examples? Well, first of all, we need to brush up on our sifting property, but I want to show you two properties of the Fourier transform that are being demonstrated here, and that is first duality. On display is what I was looking for. These properties are on display. Duality is the first one. So in this one, right, the signal is a little impulse there, just a little impulse, right, at 0. So this signal is concentrated in time, right? It's as concentrated as you can get actually in time. And then its Fourier transform is spread out. And then when we have a signal that's spread out, the Fourier transform is concentrated. So that's this duality property of the Fourier transform, which you will see time and time again working with these Fourier transforms. The second is what's called the let's see my German, Heisenberg, maybe like that, Heisenberg uncertainty principle. German, maybe? Austrian? Principle. Heisenberg uncertainty principle. So Heisenberg uncertainty principle, this is actually a quantum mechanics um, uh, law or principle, I guess. And it says the following. It says that the more you know about something in time, the less you know about it in frequency, and vice versa. So why is this a quantum mechanics thing? That I don't want to get into, but it's true here. So the more we know about something in time, so here's our time waveform in the first example, and it's very concentrated. So our signal is very concentrated in time, the less you know about its frequency, or the less features it has in frequency. Well, yeah, this is a featureless thing in frequency, right? It's just completely spread out, completely flat. And then the inverse of that is true. The less you know about something in time, so this thing is featureless in time, the more you know about it in frequency, and this thing is just a spike in frequency. That's the Heisenberg uncertainty principle.